Hello everyone. In this video we will continue to examine topic 7.1, discrete energy and radioactivity. And in particular, we will continue to unpack the mechanisms of radioactive decay. In our previous two videos, we discussed the first two primary mechanisms of radioactive decay, that is alpha and beta decay, and discovered that the true nature of an alpha particle, as it was originally characterized and described, was that of a helium nucleus. And the true nature of a beta particle was that of either an electron, in the case of beta minus decay, or a positron, in the case of beta plus decay. Our last type of decay, our last mechanism of decay, is that of gamma decay. And in gamma decay, you actually have the emission of what was thought to be a particle, but as it turns out is not in fact an individual particle, but instead just a very, very, very energetic photon. And in fact, the energies involved indicate that this photon is very often a gamma ray. This is not an accident. Gamma rays were named for their role in gamma decay. So very, very, very high energy photons. And what is happening is that a nuclide is in an excited nuclear energy level state. Now, we are not going to unpack all the things that would render a nucleus to be in one sort of energy level versus another. That would require quite a bit of discussion of the strong force in ways that are a little bit outside the scope of this course. But suffice it to say that, kind of unsurprisingly, I think, the same kind of quantum mechanical properties and quantum field theory predictions that led us to believe that there were electron energy levels also, in a similar way, lead us to believe that there are nuclear energy levels. And the particular excited states for a given nucleus are varied. But if one of those nuclei is in an excited state, then it can undergo gamma decay, where that nucleus drops to a lower level energy state, a different configuration, if you will, into what's called the ground state. So there's no change to the number of protons or the number of neutrons, or nucleon number. Instead, you just go from an excited state indicated with an asterisk to the ground state or lower level state indicated with no asterisks, and you get an emitted photon, that very highly energetic photon with frequency indicated by equals hf equal to hc over lambda. A photon, as you know, is massless. It is chargeless. But these photons have very high penetrating power, so takes a huge amount of sort of distance and or material to block them, but low ionizing power. And in fact, they ionize exactly one atom. When that photon interacts with an electron in its atomic energy levels, it can be absorbed, and then that electron has a very high energy, is now in a very, very high energy state, has a huge amount of kinetic energy. So there's an interesting sense in which gamma particles penetrate, or gamma rays penetrate, and then end up as often very, very high energy electrons, which is just like beta decay. So they're in some ways the worst of both of those worlds. And you often see gamma decays sort of after another type of decay. So for example, in this beta decay of cobalt, the cobalt beta minus decays into nickel, but that nickel is in a very, very high energy state, and because it's left in that high energy state, you get an emitted gamma as well, and that initial beta decay is followed up by an immediate episode of gamma decay. The daughter nuclide is left in the excited state after that initial decay. So you'll get these chains of decays. And in fact, take a look at these examples here, but those chains of decays are known as decay series, okay? And we'll discuss them in a later video.